In this lesson, we're going to learn to solve optimization problems. In optimization problems, we are looking for the largest value or the smallest value that a function can take within an interval. This interval is a set of restrictions to our solutions, which is known the domain of the function. In order to solve it, there are a few steps that we can follow. First, draw a diagram if necessary. Second, determine the function, which is a formula that represents the quantity to be optimized. Usually, you look at the last sentence to see what you are trying to optimize, which means maximize or minimize. Step 3, you want to make sure there's only one variable in the domain. That means you want to manipulate the equations so that there's only one variable in the domain. And step 4, you find the domain of the function to be optimized, and now we can differentiate. After you differentiate it, you let your first differentiation equal to 0 to find the critical points. And then you have to determine and identify the maximum and minimum of each critical point. And then you have to check with your endpoint to see the absolute maximum and minimum in order for you to have a conclusion. Example number 1, there is a piece of metal 60 centimeters by 30 centimeters that is to be used to make a rectangular box with an open top. Find the dimensions that will give the box with the largest volume. Step 1, we need to do a diagram. So first, we draw a rectangle and label this 60 centimeters by 30 centimeters. Second, because we need to make an open top box, that means we have to cut out the 4 corners in order to fold them to become a box. So the 4 corners that we have to cut out must be squares. And third, let's label the side length of the 4 corners to be x. Because we use the variable x on the diagram, so we have to define what x is. So we have to write a let statement. Let x represents the length of the sides of the squares at the corner in centimeter. Step 2, we need to determine a function that represents the quantity to be optimized. In this question, the quantity that we need to optimize is the volume because the question says largest volume. So even though we are finding the dimension, but the quantity needs to be optimized is actually the volume. So let's write an equation of the volume of the box. V equals length times by the width times by the height. As you can see here, there are 3 variables in the domain. But in order to do optimization, we only have 1 variable in the domain. So now let's move on to step 3, manipulating the equation so that we only have 1 variable in the domain. Let's look at our diagram again. Originally, our length is 60 centimeters, but since we have to make a box, we have to cut out the corners. That means I cut out x centimeters here, x centimeters here. So now the new length will become 60 minus 2x. Same thing again. The width originally is 30 centimeters, but I have to cut out the x here, I have to cut out the x here. So now the new width will be 30 minus 2x. And because the side length of the square is actually x, and when we fold it, the x actually becomes the height of the box. So the height is x. So now we can replace the 3 different variables in the domain into 1 single variable. After we have the equation and we have 1 variable in the domain, now we have to move on to step 4, find our domain. Domain is a set of the conditions that we have to follow. So in this question here, we have 3 different conditions. So first is the length. Length can never be smaller than 0 or greater than 60. The width can never be greater than 30 and smaller than 0. The height must be greater than 0. Now let's write it down. 0 less than L less than 60. And we know length is 60 minus 2x. Subtract 60 on all the intervals and divide by -2 to isolate for x. But when you divide by -2, the inequality sign switch. Likewise, let's do for the width. Subtract 30 on all the intervals and divided by -2, once again, the inequality sign switch. And we know the height must be greater than 0. That means x must be greater than 0. Since we have to satisfy all the conditions, therefore we can say our domain will be 0 less than x less than 15. After we find our domain, then we are ready to do step 5, differentiation. Since this function can be easily expanded, so we're going to expand it and use power rule to differentiate. After we have the expanded form, then we can differentiate. And remember to common factor them. Once we have our differentiation, then we can do step 6. Let v prime to be 0 to find and identify our critical point. Because this quadratic function, it's not factorable, so then we have to use the quadratic formula to find our critical points. Once we use the quadratic formula, we will find out it's 15 plus 5 root 3, which is approximately 23.66, which is outside our domain. So this critical point is invalid. And the other one is 15 minus 5 root 3, which is approximately 6.34, which is within our domain. So this is our critical point. Now let's identify the critical point. Let's put the v prime on, put the critical point on, and remember the boundaries between 0 and 15, and that's tested out the positive and negative sign. On the left-hand side, the critical point is positive. On the right-hand side, it's a negative. So this means function is increasing and decreasing, so we have a local maximum. At 15 minus 5 root 3, and there's a volume. Step 7, we need to make sure that this is the absolute maximum, so we have to check with our endpoints. But as you can see here, the endpoints for 0 and 15, there is no equal sign on. That means the endpoints are not being included, so it's not applicable. Therefore, this is our answer. 15 minus 5 root 3 will be the x value to have the maximum volume. Last step, we have to find our conclusions. Because the question only wants us to find the dimension, they didn't ask us to find the volume. So I just need to find the length and the width and the height by substituting the x values that we find into the length and the width and the height. After you find the length and the width and the height, remember to make a final conclusion. So you will say, therefore, the dimension of the box is length times by the width times by the height. The length and the width can interchange, but the height must be the last one.